you then. Okay,
Bye.
bye-bye. So, first of all, thanks for all of you for joining, and sorry about being late. Let me introduce me. So, I'm Marina. I will be during these 2 hours explaining a bit about blade aerodynamics, um, blade design, a bit of loads modeling. And first of all, so I'm Brazilian. I studied at the Federal University of Rio Grande do Sul. Later, I did a master in aerodynamics, like aeronautics and aerodynamics at ITA, also in Brazil. And now I'm working at Vestas as loads and control engineer for 4 years and a half, more or less. So I don't know how exactly is working. If you guys are introducing yourself, I can see here we have 19 people. Maybe we can skip and introduce later. Otherwise, can be um, a bit short on time. So I don't know if someone has any questions so far. No, I think that is a no. Please just tell me if you have any problems to hear me, or if you have any doubts, and then I can do a quick and then I can stop. Just let me put here, share my screen, and then okay. Is everybody able to see the screen?
Yes.
Okay,
Yes, it's
thanks.
okay.
Okay, thanks. So as I already mentioned, I will talk a bit about blade design turbine loads, and let me jump to the next slide. Then I divided the presentation in 4 topics. I will start with some introduction of aerodynamics, then blade design. Actually, I will talk about this later, and then I will introduce the exercise that I created for this class. Then I will introduce you to the main forces and moments and loads on turbine, and how we model the loads on a wind turbine. Okay, so probably this is already something that you heard sometimes, but the wind turbine blades works as more or less a wing of an aircraft, and we produce the energy making use of the lift of this blade, and of course at the same time we have the drag. So the combination of these forces creates then the torque and the power, and then the easiest way to model this is to use the blade element model, in which we divide the blade in small sections, and then we analyze the forces, the lift, the drag for these small parts of the blade. Probably this is already known for everybody, that the lift and the drag and the resultant force will be then a function of the wind speed that reaches this blade, and also the angle of attack that reaches this blade. The angle of attack which is between the chord of the blade and the wind speed that reaches this blade. Then going on the next slide. One thing, let me just come back here. One thing that we need to remember is that the wind speed here is not only, we need to treat here the wind as a resultant between the wind speed and also the rotor speed. And then this is what is different from, for example, a wing of an aircraft. And then once we have the wind speed and the blade speed, we need to calculate this and take into consideration the apparent wind speed, or the resultant wind speed, and then the angle that will be created between the wind speed and the blade speed. And then why this is important? Because it's probably is not something that is so difficult to imagine, that once we have the same blade rotational speed here in angles, once you multiply by the radius, we will have higher blade speeds as long as you go on the tip of the blade. So the angle between the wind speed and and the blade speed will be different from the root until the tip. And then why we need to have this into consideration, why we need to think about this? Because considering that the lift and the drag is a function of the angle of attack of our section, our airfoil, we need then to take this into consideration once we do not only the design but also all the calculations of aerodynamics, because the best angle of attack will be different for each section of the blade. Then and also for each moment, for each wind speed that this blade is experiencing. That's why then we need so a modern wind turbine will have a pitch angle and a twist angle. A pitch is that angle that changes the angle of the entire blade, and the twist will be the angle that will twist the blade for once you consider from the root until the tip, the blade will be a bit twisted in different angles in order to have the best angle of attack for each section. Then, knowing this, we need to make some considerations regarding the impact of this blade on the air that passes on this turbine. And then one very important concept that we need to introduce here is the induction. So the induction basically is how the airflow is changed once it passes a wind turbine blade or even an aircraft wing. And here, since we have a blade that is rotating, we have two types of induction. We have axial induction, which is basically the how the wind turbine blade changes the wind speed in the actual coordinate. And also we have angular induction. It's the wind speed, rotor speed that it will be added to the wind speed. So imagine that the wind is flowing, then we have the turbine here, then the wind speed after the turbine will be reduced, but at the same time, a tangential wind speed will be introduced to the flow. And then these two components we call the axial induction and the angular induction. And then why this is important? Because if we ignore this on the calculation of the aerodynamic of the blades, we'll be not taking all the effects into consideration. Actually, we will have a very wrong result. So these inductions here are necessary to estimate the maximum power that you can extract the wind and how the flow will be after the wind, the wind turbine. Sorry, I'm a bit nervous. Sorry if I make some confusions. Then going a bit further, this is also something that probably you have heard about, is the Betz limit. And then why I introduced the induction, because the induction is here the basis for the Betz limit. So without knowing the induction, without knowing that we will actually extract part of the wind speed, the Betz limit would not be calculated. And then how we calculate the Betz limit is making a relation between the power that we will extract from the wind, but also the thrust that the turbine will experience due to this extraction of the power. So making a relation between these two, the power and the thrust force, we will then be able to calculate the induction, which is basically the wind speed that we will extract from the wind. And then, because you cannot simply extract all the wind speed from the wind, we'll have a maximum induction and a maximum power that you can extract from the wind. And then this is the Betz limit. I will not go into further calculations on how we define the Betz limit right now, because probably you have already seen this, but then it's something that we might remember here, the maximum power that you can extract and the induction that will correspond to this maximum power. Okay, and then again, remembering that we have that angular induction, which is the wind speed that we introduce in an angular way, then we can make a relation between what is the angular induction for the actual induction that gives us the maximum power that can be extracted. And then between these two, we can also make some relations, taking into consideration the local speed ratio, which is this value here. And what is the local speed ratio? Basically, is the ratio between the wind speed and the rotor speed. And then this is a powerful number that we need always remember, because we can derivate and we can transform a lot of equations using this local speed ratio. And then once we make a relation between the actual induction and the angular induction using the local speed ratio, we can maximize the power production and then make a relation between these two inductions. And then here, finally, is this equation here that we have angular induction for the maximum power production. And then all of this to make estimation of what would be the power coefficient and how would be the operation of an ideal wind turbine. And then this is important to remember, because imagine that you are just starting a project and imagining, okay, I will have a wind speed that will be around 8 meters per second, and then I will have I can go up to, I don't know, 200 meters of diameter. So using very simple relations, we can have an idea of what would be the maximum power coefficient that we would have, and then the maximum power production that we would have in a simple configuration. And then this maximum power coefficient, if we just use the Betz limit, would be always 0.69. But then once we start including, for example, in this plot here, the wake rotation, the angular induction, we will start to see that, okay, it's not possible to reach the Betz limit, but then how we would be, how we would do the design of a wind turbine, trying to get to values very close to Betz limit, for example. And then we can see here, for example, that once we go to higher values of tip speed ratio, which means that once we go to rotate faster and faster, we could go and reach closer to the Betz limit. And then a person could think, okay, why not rotate faster and faster? But then we will see later that in all the process of the blade design and the wind turbine design, we need to have not only the aerodynamics into consideration, but also the operation, the noise, the material, the strength, the loads, and etc., etc. So with this, I close this very basic aerodynamics of blades, and then we can see this very, very known figure in which we define all the angles and all the forces and wind speeds that are needed to take into consideration once we are doing the design of a wind turbine blade. So here we have which is the main thing, of course, the wind velocity of the blades, in which we are already taking into consideration the actual induction that we already know and defined. Also, we have then here the rotor speed, and then we are here adding the angular induction into this rotor speed. Then the combination between these two, which is the wind speed relative, and then all the angles associated to this, which is the simplest one, the angle of attack between the wind speed relative and the chord of our airfoil at that specific radio station. Also, the angle of relative wind, which is the angle of attack of that radio station, plus the pitch angle of the turbine. Then the pitch angle of the turbine will be the blade pitch angle, that one that introduced on the root of the blade, and then the section twist angle, which already defined some slides back, which is basically how the blade will be twisting to get the best angle of attack possible. And then having all this information, having all these angles, it's very easy then to calculate the wind turbine, sorry, the blade performance for a given blade. Then this, the validity of the blade element model is that we don't have radial dependence. What does it mean? That we have a 2D behavior of the flow. So once we divide our blade, let's say in 10, 20 sections, one section will not have an influence on the next section. But then, of course, this is one thing that we are simplifying, because in the reality, our airflow will be 3D. We'll have some flow going from one section to the other, but then to start simple, we use Ben and we use these definitions. What else? In this simple blade element theory, we also don't consider tip losses. We add later some tip losses, some factors to correct the blade element. And the most well-known is the Prand tip loss factor, which basically we calculate a tip factor for each section, but then of course close to the root we will not have a tip factor. And then we start to have a tip factor added on the sections closer to the tip. Also, we have some corrections for root losses, but then here I didn't include in this slide, but I can include later. Then, as I mentioned, knowing all these angles and the inductions and all the flow, it's very easy then to calculate the aerodynamics of blade. But then, which is not easy, is to know all these variants, because, for example, the inductions will depend on the power that we produce, will depend on the lift coefficient, and the lift coefficient will depend on the angle of attack. So usually the calculation of the aerodynamics and the performance of a blade is an iterative process, and then this is what we will be doing on the later section. Okay, let me just do a break so far. Anyone has any question? Or want to share something, or did I speak too fast? No? So I think I will continue. And then, as I mentioned, the next session would be the blade design. But then I will start with this section at the end, so then we can do the exercise together. Okay? So let's
Hi,
just
excuse me. Maybe you could go a bit slower, because some of
yes.
these are a bit too technical.
Okay. Okay.
Thank you.
Yeah. Is there any point that you would like me to go again? Any specific point?
Maybe the derivation of the Betz limit, like the maximal condition, like the A times 1 minus A. That.
This one? Or
Yeah, that slide.
yeah. So yes, as I was let me just go one here, right? So basically yes, and I went too fast. I didn't explain properly these equations here. But then how we calculate the Betz limit and how we define the maximum power coefficient that we can have in a turbine we correlate the power production and the thrust on the blade because they are very similar, but the wind speed for the power production, it's a power of 3, and here it's a power of 2. And then once we correlate these two, the power and the thrust, then we can derivate and see that we cannot go higher than 0.69. And actually, the power production, the coefficient of power and the coefficient of thrust, they are a function of the actual induction. In this function, actually, we can see also that the maximum power production, the maximum power coefficient, will be at the actual induction of around 0.33. But then again, this is once we don't consider, for example, the rotation, the angular induction, the rotation that the wind turbine, the blade will introduce to the wind. So this is the most theoretical model of wind turbine is 1D aerodynamics and without any laws, any effect. And basically, it's just a relation between power and thrust that will be produced on the blade. Okay, and then once we start to take into the consideration the wake rotation, which is basically that speed that will be introduced after the wind turbine, after the wind reaches the turbine, then we start to try to calculate the angular induction. And then the angular induction will be also a function of the power, the thrust, and the torque. Now, mainly the torque. And then if we calculate the torque that will be produced on the wind turbine, we then need to take into consideration the angular induction. And because we different from the actual induction that we remove this amount of wind speed, on the angular induction we add this to the rotor speed. We add some rotational speed to our rotational speed that the turbine will have. And then that's why we can calculate the torque. But also we can correlate here with the airflow that will pass the wind turbine, and then making a correlation between the torque calculation using the angular induction and using the axial induction. We can correlate these two using the local speed ratio. The local speed ratio basically is the rotational speed and the wind speed. And then the relation between these two is at the second power. And then making some maps, of course, we can maximize here and get the best, the angular induction for the actual induction that gives us the maximum or the best power coefficient. Okay. Okay. A bit slower now. Any other question on these first topics here?
Marina,
Yeah.
You have another slide, so you can
Yeah.
go forward one more. Go forward one more.
This
Yes,
one?
this is like this one. I've been reading such an article since the last year, but I've never seen this formulation, this performance coefficient stated here as you presented. I would like to know what is the reference number 3 that you are considering here.
Yeah. So the reference number 3, it's the wind energy explained.
James
book.
Manuel. Okay, Manuel.
Yeah. Yeah. So for doing this presentation, I used mainly these three. These three first books here. They are very classical books, and then especially on the part of the blade design, I used this wind energy book because, of course, we have different ways of doing the design, different ways of making the maps for the
Okay,
calculation. But then I just followed one to be consistent.
okay, because I'm asking just to know, because in literature we have a large number of performance coefficients, and
Hmm.
and this equation that you presented to us for me is for the first time.
This one.
And yeah, this one for me is the first time. I've never see this equation
Hmm.
stated here. I've seen
Hmm.
a large equations in, for example, in my thesis, I'm using an equation presented in the book of Heyer. So Heyer, 2003, presents another equation for the performance coefficient.
Okay. Yeah.
Another question, another question to you. Uh, as you work in Vestas, uh, and Vestas is achieving a new mark on wind turbines such as 12 megawatts, 14 megawatts. Uh, do you have special equations for your blades and wind turbines, or I mean, do you have such specific equations to each kind of blade that you produce and install on the wind turbines?
Yeah. So the equations are based on these theoretical ones, but then more effects are added. And then, for example, this equation here that you were saying that you never seen, this is a operation for an ideal turbine and takes only into consideration the wake rotation. Then the tip losses and other losses are not presented here. That's why maybe if you are
Okay.
doing this for a thesis, it's maybe not the best. Here was just to show that okay, we have Bet's limit, but then even Bet's limit, we need it's not the right one to use. We need to at least consider the wake rotation. Then, for example, once we go here, and then I was following that book to more or less do a step by step on the blade design. Finally, the equation that we have here for the CP after we go into 7 or 8 steps on blade design is this one. And then we can see here that this equation for CP, then we have the local speed ratios, but also we take into consideration the angle for each of the sections. We divide the blade in multiple sections. Then and of course we also take into consideration the drag and the lift coefficients. And then this is a way more complete equation that you need to take into consideration. But of course, to calculate this, then you have already to define an airfoil, you have to define a rotational speed, so you have to be in more in not a first step of your power calculation, right? You have already to have a lot of things defined. Then regarding what we use at Vestas and in other wind turbine manufacturers, we start from these theoretical equations here. We One thing that we use a lot for estimating how good is our wind turbine blade design is the induction. So these values here that I presented here uh, for induction, like this is a theoretical limit. So this is Bet's limit and how the Bet's limit, how close we are to the Bet's limit using the actual induction, and how the coefficient changes with actual induction. So we know that if we are close to 0.33, 0.3, we have a good value for the induction. We are close to the maximum possible that we can have. And this is something that we calculate when we are doing the blade design. We plot, for example, the induction over the radius. So it's something that we use. But then things that aren't here, and I just mentioned, but we are not go to calculate here. For example, yeah, here here I included. So of course we consider drag, root losses, tip losses, blade deflection, which is basically the blades are very um, elastic. Let's say it's very easy to, you can easily have meters of deflection on the tip of your blade, and also you have a twist deflection. So once you are in operation, your blade will not have that angle that you estimate for a static blade, let's say. And then once you're doing the blade design, you have to take these two things into consideration. And then it's not easy, because then you start to have to take into consideration the material of your blade, also the how you build the structure of your blade. So this blade deflection is something that it's a real challenge, and then you need to go a bit further than the theoretical equations. And then also thermal sweep is something that has an influence on the blade, because you build your blade on a mold, and after you remove your blade from this mold, the blade can have some sweep. The blade can deflect a bit, and then you have already to know this, that you cannot just give to the factory the shape. You have to give the shape taking this thermal sweep into consideration. And also, of course, the loads on the blade and other components, vibration modes, noise, and how easy you can manufacture this blade. So, did I answer your question?
Yes, I understood what you said. Yeah, I understand because you are using an equation specifically including such a losses, wake losses. I understood.
Yeah.
Thank you.
All right. Yeah. So, I already actually started a bit with this blade design, but then we can come back to this later on. So, if anyone has any other question on blade design, maybe we can go later. I would like then to talk a bit about the turbine loads now, because the turbine loads, so the blade design and turbine loads are it's something that are correlated. And then as I just said, once you're doing the blade design, you have to take into consideration the turbine loads, but not only the loads on the blade, and not only the loads on the normal operation of the turbine. Because if you think, okay, I will start producing energy with 3 meters per second, I will go until 30, and then I will have my turbine producing the maximum power around 8-9 meters per second. Easy calculation, easy to estimate these loads. But then, in order to really install this turbine, in order to certify this turbine, you have way more situations that you need to take into consideration. And then sometimes even that you have the best design of the blade's very efficient. If the blade cannot operate in extreme conditions, and you cannot prove that this blade can operate there, you simply don't have a blade. You need to start again your design. And then this is what is done on the calculation of loads. And then if you want to know more, the main standard for load calculation is this IC 61400, which is what is used by the wind turbine manufacturers. And in this standard, we have different loads. So we have normal we have different load cases that the loads need to be calculated, and the blade and turbine need to be projected for. So we have normal conditions, operation, stop, start of the turbine. Then we have extreme wind conditions. And what is this? It's cases, for example, in which you have uh, 8 meters per second, a very normal situation, and then your wind goes up to 30 meters per second. And then your turbine needs to be projected for situations like this. Also for situations in which your turbine is operating, but then you have a fault on the system, your turbine shuts down in a strange condition, maybe with a gust, maybe with some increase on the loads, and again, your turbine needs to be projected for these situations. Of course, some situations like this are very rare to observe on a operation of the turbine, and we need to use simulations for proving that this that our turbine can operate in these scenarios. And then again, we need to do these simulations before we finish the blade design to say that okay, our blade design will be installed in a turbine and we will be able to operate in these conditions. This is for ultimate loads, for extreme loads, and also this we need to prove, we need to make our turbine, we need to project for the fatigue loads. And then here, why I think this is important to mention, because fatigue loads for a wind turbine are very different from another type of components. Why? Because you can imagine that in a normal component, you have, for example, a number of cycles that the component will be exposed during the life, and different load that will be this component will have according to the number of cycles, the classical SN curve. But on a wind turbine, maybe the biggest load will not be the load that will have the biggest impact for fatigue, because you also need to remember, once you are doing the calculation of fatigue, that you have different wind, that you have a wind distribution, which means usually you have more wind, a number of hours of wind bigger for lower wind speeds than for big wind speeds. And then even though you have higher loads on the big wind speeds, for the small wind speeds, you have more hours. So you have to, in order to calculate the fatigue loads, you have to take into consideration how different is the wind speed distribution of your turbine, and the different impact for each wind speed, the different load that this wind speed will produce on the blade, on the wind turbine. And then taking this taking the wind speed, taking the damage on the components, then you can estimate the lifetime of your turbine, or the maximum load for a given lifetime of your turbine. Too fast? Too slow? Are you familiar with this? Can I will jump to the next slide then.
Professor Yash has one question, but he
Okay.
had to leave.
Okay.
The question is at chat.
Okay. Let me. How do I see? A read one paper to failure associated with local resonance effect. Do we need to be concerned about this issue? Yeah, the blade are projected to resist, but the blades are damaged lower than some cause from effect. Okay. Yeah. Yeah, sure. We need to take into consideration resonance effects, and actually it was here the next slide. Let me share again.
For me, your slides are not be presented now.
Okay,
Okay.
now,
Thank you. Okay.
yes, and then what's here on the next slide. So yes, we need to take into consideration the resonance effects once we are doing the design, and especially we have some tricky combinations, for example, between the natural frequency of tower and the rotor speed, and sometimes the second natural frequency of tower and the frequency of the blades. So yes, resonance, we need to take this into consideration, and usually we need to avoid having these resonance loads. So let me just read again. I don't know how to, 1 second. Do we need? Yes, so we need to be concerned for sure. We need usually to avoid resonance effects, and then to avoid resonance effects, we can change the design of components, but also we can use the control software of the wind turbine. So the control sometimes can change a bit the operation of a wind turbine um, for a specific operation to avoid being in a region of resonance for one component or towers or blade or any other components. Even sometimes the shaft of the blade can, the shaft, sorry, of the blade, no, the shaft of the generator can have some resonance with other components. Um, and then the blades are projected to resist up to 8 meters per second, but the blades are damaged lower than 55. 8 meters per second, I'm not super sure. Usually, for example, in this IEC, if we go into this standard, we define the the wind speeds that we have, for example, extreme gusts in 50 years scenario. And the values that I have in my mind are around 40, 42, 48 maximum meters per second. And then it's not only the blade, but all the components need to resist for these wind speeds, extreme wind speeds. So let me just some causes from a manufacturer's perspective. Yeah, so this 80, maybe I'll ask him from where he has this information. Okay, so I think I will continue from this slide here. So again, this standard is the main used on the industry. There we have these extreme loads defined, also the fatigue loads, and then yeah, and then here okay, but what are these loads? What causes these loads? And then here I listed the main ones. So we have steady loads, which is basically the wind hitting the wind turbine. Then we have cyclic loads, and then here it's interesting to mention because why cyclic, right? Because these loads will not be the same all over the rotation of a blade. And then the main one, of course, is the weight of the blade, because you can imagine that in some positions the weight is on the same direction of the rotation. On the opposite side will be on the opposite. So sometimes the weight is helping, sometimes the weight is not helping. And once the blade is aligned with the tower, the weight is on the radial axis. Also, wind shear causes also a cyclic loading, because wind shear probably already heard about, but wind shear basically is the difference on the wind speed from the root from the base of the wind turbine until the top. So you can have differences of 3, 4, 5 meters per second in different positions of the rotor. And yeah, again, if you have sometimes the wind blowing from one side, your blade will experience different loads in one side and another side of the rotor. Then this also need to take into consideration. Then transient loads, tower shadow. The tower will slow down the wind on that position. You have to take this into consideration. Also, other loads like brake loads, in which suddenly you stop your turbine and then you have some loads because of this. Gusts, as I mentioned, we need to take into consideration situations in which the wind can go 20 meters per second up or change the wind direction. Ice also can be an issue, maybe not for Brazil, but for other countries. And also grid compliance loads, which is basically grid compliance. It's something that maybe will be explained in another section, but I can shortly describe. You have your wind turbine on a grid, and sometimes you have to decrease or increase the power in order to change, for example, the frequency of the grid. And then in these situations, you control your turbine to produce more or less, and then this can have an impact on the load. So the blades and other components will suffer a bit from situations like this. Next type of force is stochastic. So the turbulence of the wind also will cause some load, some forces. And then the resonance, as already explained, you every component will have a natural frequency, and then you need to know these natural frequencies to not have one component being coupled to other component or even with the rotor of the frequency of the rotor. And then later, forces due to control system installation and maintenance. Control system, it's something that's very, you need to have a, once you are doing the design of the blade and then later the design of the control system, sometimes you want to avoid situations of loads using the making use of a control system, let's say derating the turbine or changing the pitch, but then you can introduce other loads to the turbine. And then something that has to have a pretty well design of this control system. Also, installation loads. So imagine, and not imagine, but for example, the blades, how the blades are installed. The blades are installed one by one. So you install one blade, you turn the turbine, you install another blade, you turn again, start the third one. And then imagine, for example, if a gust suddenly hits your turbine once you're installing. So you need to calculate these loads. You need to have this into consideration once you are doing the design of the components. And maintenance again. So imagine that you are changing the pitch system of your turbine, and then you need to rotate one blade to a certain position. But then again, a gust hits the turbine. So it's very specific scenarios, but you need to have this into consideration once you are doing the calculation of your loads. Any questions here? Have someone seen any video of installation of wind turbines? If not, it's very interesting to see. I suggest we can see later if we have some minutes. Next.
For the offshore wind turbines, what would be like the new elements in addition to the ocean waves?
Yes. I will maybe put one. Oops, put one point here. Yes, then we have for the ocean the waves, and then also for the offshore, we need to take into consideration the different types of foundation. So you have if it's a floating foundation, if it's a cable foundation. So yeah, thanks for remembering. I will be adding this here. And of course, then you have to have the frequency of the waves into consideration once you are doing your resonance analysis. And then it's one more point to take into consideration.
I would like to make just a comment. Some years ago, I saw a presentation in Rio de Janeiro about infrared inspection of turbine blades, wind turbine blades. And what inspection showed that there are some marks remaining from the transportation, where the place where the turbine was lying over the truck. You could not see it during the inspection before mounting it, but it was there. So maybe there are some internal flaws that maybe during the life of the turbine, reduce the life of the turbine, the resistance against fatigue or any of these movements, because you do not see it in inspection in the visual inspection, but it is there when you watch it in the with the infrared inspection. Just a comment to share. Yes, thank
No,
you.
yeah, it's a valid comment, and um, the blades usually have some sensors all over the radius, not in so many positions, but two or three, and depends. Sometimes you have the offshore turbines usually have more sensors than onshore turbines. Why? Because you will be controlling how the wind turbine is behaving, and then, for example, suddenly you start to see a vibration there in a weird frequency that only one blade is having this, and then you can go and do this kind of inspection. This is normal because especially due to the material of the blade, which is the composite, you can have delamination, and this is a thing that's very serious, and you have to treat before the blade just um, go falls totally. Then you have the sensors for a situation like this.
Yes,
Someone,
just one question. How do you balance the turbines? Just on the weight, the blades there? Because I always have the impression that it's the same problem that you have in helicopters, is that you always have to keep it well balanced, otherwise the vibrations will put
yeah,
the aircraft down.
yes, I think I think it's less sensitive than helicopters, but yeah, once you manufacture your blades, you take three similar ones. So you weight your blades, you take the most similar ones to make the three ones that will go for a specific turbines.
To be sure that they are balanced
Yeah,
also.
yeah,
But if you need correction, there will be small corrections, not huge ones like these sailing ventilators that
yeah,
you buy some that make work like this very annoying. Okay, thank you very much. I think there are
yeah.
colleagues with more questions.
Yeah, but then also on the calculation of loads, so this on the standard, we need to take into consideration a small deviation on the weight of each blade. So it's a small factor that we always use. So if you have a small difference, your turbine will not go crazy. So if you are within a certain tolerance, it's fine. Your turbine is prepared for that. Yeah.
Okay,
Okay.
Every
thank you.
turbine, Marina, I think that every turbine has a signature vibration analysis.
Yeah.
So the balances that the professor Sergio is talking about, I think that there is a signature when the wind turbine is operating.
Yeah. Yeah. But you
Thank
mean
you.
that?
I mean
Sorry.
that the blade has a propensed unbalanced establishment. I'm talking that the blades are not properly unbalanced on the turbine, I think. But vibration will always be present at the wind turbine. So I'm talking that the, each wind turbine has each nodal frequencies to operate.
Yeah, yeah, sure. And then yeah, I think we are aligned here on the comment. And then you weight your blade once you leave the factory. You then install, and then you have ways to do some tests on the turbine to see if the estimation of the frequency is right. And then, of course, you are expect not to be wrong, but you measure this blade frequency once you install the blade. You have ways to measure this. Okay, I could see there was another person which has just 1 second. No, we don't have. Okay, so let me come back here. So here's just a visual. It's just I included here some visual representation of the thrust, gravity, and inertial forces, which are the main ones on the blade. And then thrust, that constant force from the wind, then the gravity, so which in some situations help, in some situations are not good. And then the inertial forces like the brake that I mentioned. Your turbine is rotating, and then suddenly you have to have an emergency stop, and then your blade will be stopped against the inertial forces. And then on the other components, so the other components, basically the forces on other components will be dependent on the blade and on the tower. So we have transformations of the forces into moments, and then the forces will be dependent a lot on the how you install your blades, what are the angles that you are going to install your shaft, what are the angles that you install your blades, because you can tilt a bit the blades, you can tilt a bit the shaft in order to avoid avoid risks, for example, of the blade hitting the tower, or also you turn a bit your rotor to compensate for the wind shear. So all of these angles, then in combination with the moments, will create the loads on the other components. And finally, tower loads. It's that problems of resonance are very important here for the loads. So, and also the tower loads are very sensitive on your foundation, and of course on an offshore perspective, then on if your foundation is floating or if it's cable stayed. So here, all this balance need to be considered once you're doing the design of your tower. And then later, the most important thing to take into consideration in tower is these natural frequencies, because it's very easy to be close to the frequency of the rotor or the second frequency of the rotor, and then you simply you can be close, but you cannot be operating into this frequency, or you need to use some control feature to avoid this. So basically this. It's someone would say something here? No. Then I told a lot of things about the loads, but then one thing that then I will introduce, but very briefly, because it's a huge topic, and it's how we model these loads. And then I will start with the blades, of course. So the blade, we can model a blade like a beam. So you model your blade based on the mass of your blade, the length of your blade, the inertia of your blade, and then in order to calculate the forces, the stresses, and the deflections of your blade, you can use the Euler-Bernoulli or Timoshenko beam models. I will not go so into this because I believe it's the topic for the next section. And then this is for the blades. The tower, the same way. So the tower, you also can model as a beam, but then with a mass on the top. So the mass will have the rotor mass, but also the generator, all the things that are inside the nacelle. And then the other components, usually you model as an inertia, also you need to have the transformation of the coordinates. So on the blade, you have a coordinate system that's rotating. Once you pass from the blade until the shaft, then you do a transformation of these coordinations in order to be on the coordinate system for the shaft, and then have the inertia calculated for this shaft. And then here, I just include these two drawings here to explain. So how is the model of this beam? Usually you will divide your beam into smaller sections, and then you will calculate for each of the sections the the behavior of the beam. And then yeah, and then knowing and calculating the beam, you then can estimate how will be the vibration modes of your components. And then here you do frequency analysis, and then you can estimate the frequency and the deflection shape of each of the different modes of your component. And here I included this drawing showing how is the first mode, a second mode, and a third mode. Of course, a component can have n modes, but then usually we calculate the modes until the third modes that are the second, that is the ones that have more energy and can have an influence on other components of the turbine. And then
Does the mode depend on the division in your disk, or is it independent of the division?
sorry, depending on
The mode you showed, the graph for
yeah.
the mode, does
Mm-hmm.
that analysis depend on the where you create the disk? You model it as a collection of disks?
Yeah,
Does it?
yes, here the discs that I mentioned, it's for example, the drivetrain. The drivetrain, you have you can have the gear, you have for example a gear, or in some turbines you don't have a gear, but then you have the main shaft, and then you have the generator, and then you'll be modeling this as a disk with some inertia and some connection between these disks. And then you have, for example, the inertia of the generator, the inertia of the gearbox. And then in the middle, you will have your drivetrain models, right?
Okay, then for thank you. And then for the cantilever beam, are you doing some mesh type of analysis? Are you dividing into mesh or?
Yes, then depend. You can divide to mesh, or you can do a model analysis, having estimated values for the inertia and for the stiffnesses. Depend a bit on the situation, on the what you want to analyze, because imagine that for this, imagine that you have to calculate the loads for your turbine for the most different situations, and then you have, let's say, around more than 20. Yeah, it's written here. More than 20. You have 20 to 30 design load case that you need to comply, and usually you use simulations to prove that your turbine can be designed. And then each simulation, you have then a couple of different wind speeds that you have to simulate. Then in the end, you have more or less 6,000 simulations that you need to perform and analyze in order to say that, okay, my turbine it's something that can be projected, can be designed. And then you use you want to use simple models in order to do this in an efficient way. But then you can have, for example, a situation and then that you need to analyze if you have or not a resonance problem. Then you can do a more detailed design using meshes, for example, using smaller elements, and um, instead of using model analysis and looking at a component only as a mode and a, and a deflection, really resolving every small piece of this component. So you use both in the end, depend on the application. Did I answer
Okay.
the question?
Yes, thank you.
Yeah. And then more or less on the same topic, then this model analysis. So we then will be modeling the different components as a simplified model, and the objective is to know the natural frequency of the different components and how these components will deflect and how they will perform. And then, because what we need to know if one component will have a natural frequency similar to other component or to the rotor, and some already mentioned. And also we need to know the damping of these different components. Why? Because sometimes we can have natural frequency close to the rotor, let's say a tower close to rotor, but then we need to know if the damping, if we have enough damping on this component, or if this component is already close to a negative damping, which the component will just resonate. So these analyses are done using this model analysis, and then here included the main ones, the main software that are used for loads modeling. This FAST is open source, so if anytime you want to try, you can go download, and you have a couple of models that you can download and model on your computer and see if you can get results. Also, there are some models from FAST to MATLAB. Then you can, for example, have a rotor and then try to do a model of a tower, for example. So it's for if someone wants to go into this loads modeling, it's possible. And then, okay, and then here I have all the references. I also included on the slides some additional material. There is this wind energy course from DTU you can do on Coursera. There is also some lessons on the YouTube. It's a very good one if person wants to go deeper. And here, yes, here has included a reference for some exercise on MATLAB. Okay, let me just see. So we have 45 minutes for the loads modeling. And does anyone has any other question on the topics so far?
Yes.
Okay.
Hello, and Carlos.
Hi.
Hello, Marina. So you showed actually a step-by-step process, right? Where you do, for example, the static loads, and then you analyze fatigue and so on. Are you at Vestas using any kind of MDO technique, like a multidisciplinary optimization, so you can assemble a framework and do everything on like at once? Are you? This is just a question about your actual job at Vestas, or how things are done at Vestas.
Yeah. So you have what can called user cases, in which you have to comply, let's say, wind turbine that we have, as already mentioned, 15 megawatts, for example, need to comply, and it's designed for mainly three different markets. Let's say you have Asia, you have Brazil, and you have north of Europe, and then you know that your climate will have some different characteristics on these markets. And then in the end, what you need to do, you need to create a scenario. It's three different scenarios in which you have to comply. And then this needs to enter into consideration. And then MDO, like you mentioned, is done based on the scenarios that you have on the markets that you have for your turbine, but also on the possible markets, because you can have three main ones, but you have to consider all the other ones. So you can optimize.
Oh, okay, yeah, but it's still for the blade, because your topic is about the blade. So yeah, for the blade, this blade for all machines, because maybe the control system, and I don't know, so
Hi,
For example,
Carlos?
you do this 6 or 500. I don't know.
Carlos? It's only for me.
Uh,
For me too. I
very
cannot
Ah,
hear
hello,
Carlos?
poor connection. Poor connection
Yeah.
here.
Okay.
Okay. Okay, sorry. I know my tablet here, and it seems that Wi-Fi is not good.
Oh, no, fine.
No, it's just a question of if you have any kind of MDO framework for the blade itself. Like,
Yeah. Yeah. Maybe I went too far, but this is also need to be considered for the blade because the markets that use sell the turbine will in the end have a direct effect on the blade design because you have different, for example, average wind speeds that you need to take into consideration, and then but sometimes you okay, perfect, I have the perfect scenario, but then you have also to take into consideration transportation, and
yeah, okay,
then
but still, it's still just a question about, do you have any MDO framework working or not? You do it step by step,
it
even
needs
if
to
you
be,
have different scenarios.
yeah, need to be done step by step with different considerations. So because transportation can be a issue, and then you need, for example, to split your blade into two pieces. Because, for
No,
example,
yeah.
in some,
For example, in the aerospace area, you have some standards for
yeah,
transportation loads. You have to calculate that
yeah,
also. But no, I'm asking you because then it looks like there's a field of research, right? If
mhm,
you in the industry is not using an MDO, like you're not telling me yes, you're telling me that perhaps. So I see that it might be a very interesting field of research, like create an MDO as a framework for blade design, especially for offshore turbines.
mhm.
Okay, yeah, what do you think about?
Yeah, can be an interesting. Um, I I I cannot say that we don't have at all. There is some optimizations on the design, of course, but I think it's a bit different from aerospace because in aerospace, for example, you don't have so many variability to the to the climate conditions, for example, as you have.
I don't believe so. The airplane will fly everywhere around the globe. Okay,
Yeah,
it can fly. It can
no,
fly
yeah,
from Mato Grosso to Canada, for example. So
yeah,
Embraer
yeah.
has to take account of that.
Yeah, yeah, yeah. I worked at Embraer as well, and I was working with MDO there sometimes.
Yes, I know.
Uh, yeah.
Okay, good.
Yes, but then, for example, here we the wind average, it's something that has a huge impact on the blade design, and then different from an aircraft that can fly, but here the weight of the blade, the loads, all of this will have an
Yeah,
influence from the
but it's still all of this variability can be taken account
yeah,
into MDO. Okay, yeah. So
yeah.
I don't know who you work with there at Embraer. I know some people there, but still, okay. So I think that your answer is I understood. Thank you.
Yeah,
I don't want to take longer.
no, no, it's fine. I think can have some room for improvement. Um, but then it's not that it's not used for at all. It's just that you have maybe a bit more variables that sometimes are a bit difficult to put in an optimizer. Because, for example, this thing of the transportation, uh, if you need to split your blade into two pieces, then you need to restart the blade design from the beginning because
Yeah,
the
but
blade
it's
design will
still,
be
I think
completely
that
different.
this is the challenge of the MDO, right?
Yeah.
So in terms of research, of a new research, if you think that something is difficult, then it's a challenge for someone to study it and simplify it and make it done. Okay, so yes. Okay.
Yeah, for sure. I think there are room for
Everything that is
improvement.
difficult. Yes.
Yeah. Hello, I think
Okay,
it's
thank
feeling
you.
a bit again. Okay. Yeah. Um, anyone has another question? No. So I will just see how can I share the blade design exercise with you. 1 second. If I send here on the if I send here on the chat, do you receive? Let me try. 1 second.
You may share with us by the chat, and we can download it.
Okay. Yeah. Okay, 1 second. So let me just take here. No. Um, um, I don't. I don't know why I can. It's not appearing for me to attach here. Yesterday, how did Sarah send you like this? Or did she send you?
She shares a link for the
Ah, okay. Maybe I can. Yeah, maybe I can put here.
You have to upload on Drive
not the file, just the
and
link.
send the link to us.
Ah, okay. Good. Okay. Let me then. Ah, yes. She created a shared folder here. Right. Exercise. Okay. Then. Let me. Mm, 1 second. Sorry, I'm. Okay. Now shall work. Okay. Can you try the link here? If it's working. Did someone already tried?
Yes, it worked. Thank you.
Okay, nice, nice. So, okay, I will share and then you can follow the, basically here, I decided to do this exercise in Excel because I think we have for the aerodynamic design of the blade, if you search on internet, we have different softwares and you can have way better softwares. But I decided to do this in Excel iteratively because then you can follow the equations, you can follow the step by step, and you can even do some, for example, improvements and add more effects, for example. And then I will share again the presentation, and then you will be able to follow the equations, and they are already implemented here on this exercise. So let me just explain a bit the simplifications that I did. So I included here only one airfoil. Of course, on a wind turbine blade, you have different airfoils, but I decided here to include only one just for simplification. But then having this Excel later, you can define different airfoils and see different possibilities for a blade. And then here on this tab is where we have this iterative process. So in yellow are the variables that you need to define for your design. Basically, the power, the wind speed, and then has an estimation of the CP, an estimation of the lift coefficient of design, angle of attack for design, number of blades, number of elements in which you will divide your blade, and the tip speed ratio that you want to work with. And then based on these equations here that I will present, then you can estimate the performance of your turbine, of your blade. Okay, then let me come back here to the part of the blade design. So as already mentioned, due to some questions, of course, here I'm following a simplified blade design method based on a classical book, but is the theory that the real design is based. And then here, one thing also to separate is the blade geometry and the structural design. So here I will present the blade geometry, which is the part that we define the airfoils, the core distribution, the twist, all this aerodynamic shape of the blade. Then at more or less the same time, you have the structural design because of course, this blade will create some loads, and then the structural design need to follow this design in order to make a feasible blade. But then this is done separately. Then first thing is to define the point of project. So for which wind speed you're gonna do the design of your blade. Of course, your blade will operate from, let's say, 3 to 30 meters per second, will produce energy, but you have to define a specific one for which your turbine will produce the rated power and the one that your turbine will be designed for. And then here, one thing to take into consideration is the ratio between the wind speed rated and the wind speed average. The wind speed rated is this one that we'll be doing our project, and it's the wind speed in which you have the rated power, which means the power that you are designing your turbine for. And the wind speed average will depend on the sites, on the climate that you are designing your turbine. Of course, again, your turbine can operate in different for different wind speed averages, and you can also use the control system to compensate for this. But the initial guess, it's interesting to have more or less a range of the ratio between these two wind speeds. Then you can have different ways of operating your turbine. Of course, the normal ones, you have pitch system, then you have a control system that usually will maintain the tip speed ratio, that ratio between the rotor speed and the wind speed at a constant value for different wind speeds, which means your generator speed will be changing for achieving the best tip speed ratio for the operation. And then the pitch system later will be adjusting the operation of your turbine to be at the rated wind speed. In the past, there was the stall control turbines, but nowadays on the modern design, it's the pitch system and the turbines that have the constant tip speed ratio that are the main ones, the baseline ones on the industry. And then this part already mentioned, so you have the theoretical, the theory, this more theoretical design, and then later you will be adding the different effects that will have an impact on the final blade shape and the final blade design. And then here, yes, so I'm following one reference, and then the first thing is defining for which conditions you are going to design, for which tip speed ratio, which is the power coefficient that you will use as a first guess for your turbine, and efficiency for the other components. And then here, the tip speed ratio, as already mentioned to you, will have a direct influence on the power coefficient of your turbine once you include the wake rotation in your calculation. And then let's say my first estimation can be a tip speed duration of 10. I can because it's the one that goes closer to the BETS limit. But then later on the design, maybe I will have noise requirement, something that defines that I cannot go upper on the rotor speed, but I can always start my assumption with the best possible tip speed ratio for my case. Then next thing is define the number of blades. So here you are free. You can design a wind turbine with one blade, let's say, but of course 3 is the main one on the industry. And then next thing that you need to define is airfoils. As I already mentioned, I chose one, but usually you have different ones because also you can imagine that at the root of the blade you have a cylinder, and then you need to transition from a cylinder to a more efficient airfoil, and then close to the root you have higher thickness over ratio airfoils with high thickness over ratio, and then later you'll be reducing this in order to improve the efficiency of your airfoil. Then here first thing is dividing the blade into a number of elements to be able to use the blade element model. And then for each of these elements, we will be calculating the aerodynamic for the small pieces of the blade. And then, of course, all of these equations are already they are already defined from other equations. Here I'm presenting you, for example, the angles based directly on the local speed ratio. But then in order to have this equation, there's a couple of others, but I just put the final one to do here the step by step. Then you define the local angle between the chord and the resultant wind speed. Then the next thing that you define on this step is the chord of the element, and here the chord basically it's a direct function of the coefficient of lift because you need to achieve a certain power at that element. And here you define a coefficient of lift of design. Then later you have here the pitch, the twist angle, which is a function of the pitch and the first pitch of the blade. And then the same way you have the angle of attack that will be dependent on that pitch angle for that element of the blade. Then in order to solve this, you can linearize these equations and then solve using different methods. If we go into this book, we have different methods, but here the method that I chose was the method that uses the axial and angular induction for solving these first equations here. Because, as I mentioned to you, the inductions will be changing, uh, dependent on the rotor speed that you use, dependent, for example, on the lift design that you use. And then here, you can solve, for example, in other method for the lift coefficient, but then the method I chose was using these inductions. And then you will define a first guess for the induction. And here I think, for example, I already did a first guess of 0.3 and 0.5 based on this plot here that are closer to the Betz limit. And then yeah. And then once we have the first guess, then we calculate again the induction, and then we go back to the first equations. Then we will calculate the angles based on these inductions, the tip loss that we will have for each element of our blade. Then later lift and drag coefficient, thrust coefficient, and then the induction for the next iteration. And finally, the power coefficient for that element and for the whole blade that will be used again on the beginning of the iteration, right? Then going to the exercise here. First thing is defining these main characteristics of your turbine. Then I already introduced here the equations for each element. I divided the blade in 10 elements actually. The angles for the relative wing, then the section pitch angles, the section twist angles, and then here the way of solving for the inductions using a first estimation of axial and angular induction. And finally, we recalculate the induction for the next iteration. And then here, my idea is once we define the axial induction and the angular induction, we can duplicate this tab, introduce these values here on these lines. Once we reach a difference between these values that's close to zero, very, very close to zero, right? Of course, if you want to implement this on MATLAB, Python, it's also easier to do this iterative process. But then I decided here to implement on Excel to be able to have something very visual. Because then my idea in the end is that we can produce plots like these ones here with the chord distribution and the blade twist distribution, and then we can compare and see how close, how far we are from what, for example, is estimated here. Okay, so I think if you someone already started here to fulfill, but maybe my suggestion would be for you to download this and to then try to see if you can reach those plots, and then I will be here. Or guys, do you prefer to fulfill together and see? For example, how Sarah did yesterday? Did she fulfilled with you, or every person did by yourself?
Excuse me?
No. So how Sarah did yesterday? Did she fulfill together with you? Okay, Sarah gave us some time.
She just gave us some time to do the exercise.
Okay. Okay, so we can do, I can give you 10 minutes. I think is nice. Then you can go and explore a bit. And then in the end, we can do together and compare the results. What do you think?
Thank you.
Okay, then we
Okay.
can, I saw someone already started with a certain power. We can define a certain power in a certain tip speed ratio, or we can, for example, compare different designs.
I always use it tip speed ratio of 7 for 3 blades wind turbine. It's okay.
Yeah. Okay. Yeah. Okay, then let's have 10 minutes. Then we can come together and compare the results that you have. If you can download the the table, then we can see if you guys manage to find a solution. There is one final equation that is missing, which is the final CP. Then also, yeah, was actually my idea to ask you here to implement this latest equation here and to restart the next iteration. So if you can if you manage to come until here, then we can maybe start from this point together. Okay, so in 5 or 10 minutes, then we can come back together. So anyone already found a solution?
Hi, Marina.
So I think I will just let me come here, and I will
A good difference for induction factor is about 0.0001 or less. It's okay.
So I was doing the exercise on my side earlier, and then, for example, I stopped when I had induction, a different, especially on the actual smaller than 0.001.
Okay.
Yeah, and then, but the thing that I saw changing mostly was the CP. I don't know if you guys already managed to calculate, but I don't know why I cannot introduce here on the
I put
spread.
the CPE about 0.3 because it's near the hated power. It's not
Yeah,
so good. It's okay?
yeah,
Or
yeah. Yes, exactly. So, and then the first thing I could see was that my estimation of CP was too optimistic. And then I think was one point that I was aiming to discuss, because we think, okay, the CP of we can go close to bat limit. Yeah, but then you have to have a very good design. And here with only one airfoil and with a lot of small assumptions, the values we have is close to 0.3, more than 0.69, 59.
okay,
Yeah.
okay.
So I think you got my my idea.
Yeah.
Yeah. But then
And the angle of the aerodynamic profile, I adopted something about 4.5
yeah,
for
yeah,
the
yeah,
dollar.
yeah. It was what I was considering. I was trying to I didn't implement a lookup table on the CL and CD. Would need to implement there a lookup table on the CL and CD in order to iterate again. But then I was just going there and looking at the table.
You may share
Yeah,
your
so
Excel with us.
yeah. So let me uh, just adjust one thing here. I'll come back in 1 minute. Okay, let me share here. So the exercise I was doing, I was actually considering wind turbine with share. Here. Okay, so I was actually doing for a wind turbine of 7.2 megawatts. And then I was actually considering a tip speed ratio a bit higher, around 10. And then angle of attack of 4 for design and 3 blades. And then here on the first calculation, and then including that equation for CP that I already mentioned, then the final CP that I got was 0.36, which is way far away than my first assumption, which was 0.59, very close to that limit. So said Marina goes and copy this and do the next. I cannot copy. Duplicate here. And then my idea here, okay, I can go here and now 0.37, then we 0.0, 37, and then we can see first thing, a huge difference on the radius and the emitter that our turbine need to have in this next iteration, right? The previous iteration, we had 72 meters of radius, now 91. So first thing that we can see. Then, if we don't change, for example, our angle of attack of design, neither our lift coefficient of design, and we just take these values here that we just discovered for the actual induction, and we then introduced here, then okay, we can go and have the values for the next iteration. Then we could see that the CP increased a bit. Then here, I think in four or five steps, then we could reach a feasible design. And then that was my intention with this exercise. We do one at a time. Then of course we could adjust the angle of attack or the CL just to see if we can get better results. Then that's what was my idea on this exercise. Questions? Any concept that maybe I need to go back in 2 minutes to explain better? One thing that one concept that I didn't touch, but it's quite important, and it's here. It's the solidity. Solidity basically is the how much of area you have with blades on your disc, and then it's something that is also one parameter of design, one parameter of performance of design of a blade that we can check. And then finally, here I think with 2 or 3 iterations we could do that plot showing the chord and the angle of attack or angle of twist, actually. Sorry, the angle of twist for a blade design. Any question? We actually.
Excuse me.
Sorry. Yeah.
We may redefine the angle of at this yellow cell, or just here to calculate and see what happened, or we have to correct that.
Yeah, here for the first time, once we change here the angle of attack, then you can see here you'll be changing the section pitch angle. But then what I tried to, and I don't know why my lookup table was not helping me, was again changing this LCD. And then, for example, if I change to 5 here, I would have to come here and put the 5. So yeah, it is something that I would have to see exactly how the lookup tables work here. But yeah.
Nice, very nice. Thanks.
Yeah, of course, implementing this into MATLAB or Python would give us faster and more efficient code. But I think just for having an idea and having like familiarity with the equations, I think the Excel can already provide nice results. Okay, so I don't want to go further because Wilson and Eloisa has their section now. I think you have my email. If you have any question or any point that you would like to discuss with me, it will be a pleasure to hear from you. And also, if you by any chance get to a point that you finish this exercise, also I will be happy to see the results. And yeah, it was very nice for me giving this class. Sorry about the beginning, I was a bit nervous, but I think in the end we all understand each other. Wilson?
Thank you
Just
very
want to
much.
give applause.
Okay.
Just a small question. For the wind speed for design, you gave us as starters 10 meters per second, and this is 36 kilometers per hour. And we have here where I live, it's about 20 very often. I can just take the wind chart and take the maximum for the design or the average speed. Because I always say that here in Osório, 360 days of the year we have strong wind, and the other 5 is stronger. And this afternoon we are expecting wind velocities of 18 to 20 meters per second, maximum, and this is quite normal here. And what is the criteria? You see, it seems to me very too simple to look at the wind chart and say, okay, here for this city, I will take this speed. But in this case here, what will I do? We have now less than 10 meters per second, and in the afternoon, 18 meters per second.
Yeah, I think you would have to consider the wind speed distribution. So how is the probability of the different wind speed? Also the wind rows, because you have a section of more interesting than the other. And then what I found was this relation of this relation between the wind speed rated and wind speed average of around 1.6, 1.4.
Yeah, okay.
Yes.
Okay. Because if you go from 10 to 20 meters per second, you dramatically reduce the diameter of the rotor from 170 to 70, 80 meters. And this is a huge difference in your choice and in the final price of your turbine. Yes, because you have smaller blades, but at the end the efficiency goes down.
Then you need then I think you can go back to the AP calculation of that Sarah did yesterday. Then you need to consider, okay, you can have a rated power and a rated wind speed of 25, but then if you only reach 25 3 days of the year, in the end is not a good solution then.
Yes, okay. Okay, the answer is measure.
Yeah.
Okay.
Yes.
Thank you.
Measure wise and decide. Yeah. But thanks a lot for very good questions. And okay, I already took 5 minutes.
I thank you.
Yeah. Bye-bye.
Bye. Thanks.
Bye-bye.
Marina.
Thank you very much.
Bye, Marina. Thank you.
Okay.
Bye.
Bye. Thank you.
Thank you.
Hello, everyone. Now is our session. I hope you are super motivated. First of all, good afternoon in Brazil, or good morning, good afternoon for those who are joining from Central European time. I will propose a 5 minutes break so you can take a cup of coffee, fresh breath, and then we come back 10 past. Is it fine?
I thought you brought some
Thanks.
beer.
Great. See you in a bit. So, is everyone there? Hello? If you can put a thumbs up.
Yeah.
Yeah. Great. I can see Marina is also put with the thumb
Everybody's
up.
back.
Everybody's back. Great. So everyone, we have one disclaimer for this session. Unfortunately, we will not be able to record this session. So all the material here that we will present has copyright. So I hope you